All right, let's think of another example now that's going to help us to define something else that's important. So I'm told that it's quite cloudy in Seattle, so you have to be okay with that if you're going to live there. So let's ask the question, what's the probability that it's cloudy in Seattle on any given day? All right, so that's a question we will ask here. Now, what's the event space? Well, if this is the only question I'm trying to answer, then there's really only two events. It's either cloudy or it's not, right? So I'll just say cloudy, not cloudy. All right, so I looked it up, and apparently it is cloudy. It is indeed cloudy quite often. So it's cloudy 308 days of the year. So if we write this as a probability, it's a proportion, right? So out of the whole event space, well, there's 365 days, right? Out of those 365 days, we'll carve out 308, and we find there's a cloudy. So what we'll say is the probability that's cloudy is equal to 308 over 365. Well, if I bring up my trusty Python here to help me do some arithmetic, then I will find that 308 over 365 is about 0.84. Okay. So let's just round it to 0.84 as a probability. Now let's make a Venn diagram for this. So I would draw this event as being fairly large, right? Taking up quite a lot of area. If I threw a dot at this, if I threw a dart at this board, it would be quite likely that it would hit on this oval that has cloudy here. Outside of that, though, there is still some room for a perfectly sunny day. So outside we'll say not cloudy. And what you notice about these is these events are what are known as complements of each other. So one thing you can say about complements is that P of not cloudy is equal to 1 minus P cloudy. So in particular, if we look at the number of days that are not cloudy, it's going to be 365 minus 308. Let's go back here. And we end up with 57 days. Okay, so 57 over 365 is 0.15, which I'll round up to 0.16 so that I'm consistent here. So I find that probability that's not cloudy equals 0.16. Well, is that true here? Yeah, well, 1 minus 0.84 is 0.16. Okay, so these events are called complements of each other. So that's a useful thing to know. Just to sum this up in general, what it's really saying is that the event and not the event covers the entire event space. So in this case, there were only two events, cloudy and not cloudy. But I definitely could have divided up not cloudy into maybe sunny and beautiful and sunny and hazy. So in that case, not cloudy is actually a little bit more granular. Perhaps it gets split up. And on this side, it's sunny and hazy. And on the other side, it is sunny and beautiful, right? Okay. But, and let me make this just a little bigger so I can put that in there. But taken together, these are both not cloudy. And so what I'm saying in general is that the entire event space is covered by an event and its complement. So the probability of an event plus the probability of not the event is equal to 1. Okay, so that's true. And you see this is just a specific example of that. All right, let's look at an example that's super relevant to us right now. So let's create an event space out of all the students that are Sinus in 300 or 400 level CS courses this fall. All right. So let's assume this is about correct and maybe a slight overestimate, but let's assume that there are 50. Okay. So cool. So we got 50 students just to make the numbers nice and round. Okay, now it turns out I have 30 unique students. So what we can say is the probability that upper level CS student is taking a class with me is equal to 30 over 50. So chances are, if you were going to randomly choose a student who was in this category, they would be taking a class with me. All right, so that's cool. We can actually get a little more fine-grained. So what I can say is that there are 22 students in this class in CS 477, which means that the probability, if you were taking a 300, 400 level and you ended up in this class, would be 0.44. So that would be 22 over 50, right? And I also have 16 students in theory of computation, which is awesome. Very happy with that. So in that case, I would say that the probability is 16 over 50, which is 0.32. All right, now let's go ahead and think about, well, what is, again, let's try to just look at this information here and say, can we figure out what's the probability that an upper level CS student be taking a course with me? So if I try to just say probability of CS 477 plus the probability of CS 373, I would get 0.44 plus 0.32, which is 0.76. But that contradicts what's written up here, doesn't it? That something doesn't add up properly. And what's the reason? So pause for a second to think about it. Well, some incredibly lucky students had me for both CS 477 and CS 373. See how lucky they are? So there's actually overlap. In particular, there are 8 students in common between these two classes. So 8 over 50 is 0.16. So if I add these together, 0.44 plus 0.32, what I'm really doing is I'm double counting students who are both in 477 and 373. So what I have to do is subtract that overlap, which again is it's 8 students, 8 out of 50 is 0.16. If I look at this, I get 0.76 minus 0.16, and then I correctly get 0.6. So to draw this out as a Venn diagram, what we're really saying is if we have two events that overlap each other, so this is what this looks like. So here we have event A, and here we have event B. And this is A and B in the middle. So what we're saying is that the probability of A or B, so that one or the other happens, and it could be both, right? It's consistent with the kind of ors that we do in our if statement. So the probability of A or B is going to be equal to the probability of A plus the probability of B minus the double counting that we do. So minus the probability of A and B. So in this specific example, I would be saying the probability that you're with Prof. Traley is equal to the probability that you're in CS 477 plus the probability that you're in CS 373 minus the probability that you're in both. So that's what I just did up here, if you plug these numbers into the equation. All right, so we have to be careful when things overlap. If you just add them together and you don't take into consideration that there's this overlap, then you're probably going to get a wrong answer. Be that as it may, there are actually certain cases where you can simply add the probabilities together to get the OR. So these are called disjoint events. And as an example of this, let's consider an event space, which is all CS students in Pennsylvania. Okay. So if I ask the question now, well, what's the probability that you're taking this class at Ursinus, or you're taking a class called CS 317 at Bryn Mawr, which that is their animation class, which is being offered this semester. Well, in this case, it turns out that I actually can add them together because there's no overlap between the two. So I can just say, well, that is going to be the probability, given that you're a student in PA, and I'm going to carve out a part of the event space that is unique to Ursinus and a part of the event space that's unique to Bryn Mawr, and there's no overlap. So I can add the probability. So drawn as a Venn diagram, we would say, okay, over here we've got this tiny little, I'll draw it a little bigger than it probably is, but here's our sinus. And over here is probably a similar size for Bryn Mawr, maybe even a bit smaller. And there's just no overlap between any of the students enrolled at either of these colleges. So we can divvy these up any way we want. So here's like AI, here's 373. Here's databases, right? There's probably overlap between all three of these. We can divvy up Bryn Mawr any way we want, but if we pick out, just 373 over here, we see that it's totally disjoint from, or 477. We see it's totally disjoint from 317 over here. So we could just figure out, well, what is the area for CS 477, and simply add that to the area for Bryn Mawr. All right, so when there's no overlap, we call these disjoint events, and it's much easier to just add them together. We don't have to worry about the overlap. All right, so I'm gonna have you do just a couple little exercises to make sure that you comprehended this, and then we'll continue.